Okay, today we're going to talk about quantum information theory. These lectures are going to come from lecture notes by Vern Paulsen from the University of Waterloo. This is going to expect knowledge of functional analysis to some extent. It's also going to expect some knowledge of complex analysis and algebra. So let's start with the background, and we'll get to some quantum theory today, but not much. Okay, some basic definitions. C is usual complex space. Now, if P is a natural number, Cp we're going to consider as the n-dimensional vector space over C, which is just the set of vectors lambda 1 up to lambda n, where lambda p, where lambda I is an element of C for 1 less than or equal to I less than or equal to p. So really the vectors we all know and love. Okay, this has the canonical basis EI, which is the vector with a 1 in the ith row and zeros everywhere else. We will also call this ket I. This is called ket in physics notation. Okay, we are then going to talk about M and P, where N and P are natural numbers. These are going to be the N by P matrices over C, complex numbers. Really, we're not going to show the C because we're only going to be talking about the complex numbers. So we will always just say M and P. Now we're going to identify M and P as the linear operators from Cn, from Cp to Cn. How will we do this? Well, take a matrix A, an element of M and P. Then A is going to be the elements in C, Aij, where 1 is less than or equal to I is less than or equal to. So this is the number of rows. There's n rows. 1 less than or equal to j less than or equal to these are the number of columns. This is n rows, p columns, less than or equal to p. Okay, then we're going to say if A acts on this element of Cp, so lambda 1 down to lambda p, this is just going to equal, this is going to be a vector in Cn, some A1 I lambda I equals 1 to p, all the way down to the sum I equals 1 to p, An I lambda I. So this has p rows, so it's an element of Cn. Okay, now we're going to also say A star, so the adjoint of A, for those who have functional analysis knowledge. In the case of matrices, we can just think of this as A, J, I conjugate. So we take the transpose and we conjugate element-wise. Now you can't necessarily say this in general, but for just matrices in finite dimensions, it's okay. Okay, and we're also going to, so here we had bra I. We're going to say ket j, this is going to be aej star. So if we look at this, ej star, it's going to have, where ej had columns, this is just a row, this is 0, 0, 1, 0, 0, where this is the jth position. Now, Eij is going to be j, so bra j, ket I, this is Ei star, Ej, so this is actually an element of MNP. This is going to be 0, it's going to have a 1 in the ith row and jth column. So let this be the jth column. There are n times p of these, and MNP is an n times p dimensional vector space, so this is the canonical basis. Okay. So now that we understand the vector space we're working with, have decided our notation, let V and W be vector spaces. Let's say V is just CP and W is CQ. We can identify V direct sum W with C to the P plus Q. Now we will do this by taking lambda 1 up through lambda P. This is an element of CP. Mu1 up through mu q. This is an element of CQ. This is going to map to just the vector lambda 1, lambda p, mu1, mu q. So this is an element of CP plus Q. Now we're going to just consider these equivalent many times as we talk about it. Like this, we will identify LCP1, CP2, CQ1, direct sum CQ2. So the linear operators from CP1 direct sum CP2 to CQ1 direct sum CQ2, we're going to identify this with LCP P1 plus P2, C Q1 plus Q2. In this, as we saw before, is identified with M, P1 plus P2, Q1 plus Q2. No, reverse that. Q1 plus Q2, P1 plus P2. You reverse these. Because you want to end up in Q1 plus Q2 dimensional space. Okay, so if you have an element of MQ1 plus Q2, P1 plus P2, you can write this A equals A11, A2, A12, A21, A22, where Aij is an element of M, Qi, Pj, where I and j are elements of 1 and 2. So equal to I. You can think about doing this for an arbitrary number much the exact same way. These are called block matrices. Okay. So now that we understand direct sums, let's talk about tensor products. So direct sums let you add the vector spaces. What if you want to multiply? First, we must talk about what it means to be bilinear. Okay. Let V, W, and Z be vector spaces. These are all over C. So, we're going to call a map B from V cross W to Z bilinear if for V1, V2, V, element of V, W1, W2, W, W, alpha, and C, we get B of V1 plus V2, W equals B V1 alpha V2, W equals B V1 W plus alpha B V2 W. That's linear in the first. B V W1 plus alpha W2 equals B V W1 plus alpha B V W2. That's just W. Sorry about that. So it's linear in the first and second coordinate. So now we remember from our algebra, we're going to have V tensor W equals the set V tensor W, such that V is an element of V, W is an element of W, and tensor is bilinear. So, what you really want is if V is, so it's the unique space where if B from V cross W to Z is bilinear, then there exists T from V tensor W to Z where V cross W through tensor to V tensor W down to Z T B commutes. And this is true for any bilinear map B. Okay. Let's get more space again. Now, suppose you have a basis for V and for W. Let Vi for I in some index set I, and Vj, where j is in some index set j, be a basis. This would be Wj. This is a basis for this for V and this for W. Then the set Vi tensor Wj, where I is an element of I and j is an element of j, this is a basis for V tensor W. Okay. If this is a basis for V tensor W, then the dimension of V tensor W, well, these are all unique. So you get this is the cardinality of I times the cardinality of j, which equals the dimension of V times the dimension of W. So you use direct sum to add and tensor product to multiply. Okay. Now, if U is an element of V tensor W, then we get two different things. One, there exist unique we call these xj's. Xj's in W, where U equals the sum, J an element of J, Xj tensor Wj. In this way, we get V tensor W is isomorphic to W direct sum V direct sum V direct sum V cardinality of J times. This only works if it's finite. Does it work if it's infinite? Yeah. Okay. We're mainly only talking about finite spaces in these lectures. We also get, if it's true for the first, you would expect it to be true the other way around too. Here, we're looking at the v side, with the wj basis. We would expect to flip it as well. And as we would expect, we get there exists unique yi in W, where u equals the sum of vi, I, an element of I, tensor yi. In this way, the tensor W looks like W direct sum W direct sum W. This is the cardinality of I times. So it works both ways. Okay. Now we know that finite dimensional complex space is unique up to dimension. We know Cn tensor Cm is isomorphic to Cn times m. We showed that with our basis. Now, there are two ways to order Cn tensor Cm. The first way, we could do E1 tensor E1, E1 tensor E2, E1 tensor Em, E2 tensor E1, all the way up to En tensor Em. In other words, we take Ei tensor Ej, and we map this to Ep I minus 1 plus j. The other option is we could order this E1 tensor E1, E2 tensor E1, E2 En tensor E1, E1 tensor E2, all the way up to En tensor Em. So first we increase the first. So Ei tensor Ej, this should be P, this should be M. Ei plus N J minus 1. In this way, we get the isomorphism from Cn tensor Cm to Cn times M. So this gives us a nice shuffle. We could go from Cnm to Cn tensor Cm. We could do this by 1 and go this back, Nm, by 2. This is called the canonical shuffle. Okay. So now we know what our vector space is, our direct sum, and our tensor product is. Okay? But really, we want more structure than just a vector space. Don't get me wrong, we love vector spaces, but we want more. So what extra structure do we want? What we really want is an inner product. So, what is an inner product? Let V be a vector space. Okay? Let V1, V2, V, W1, W2, W be in V, and alpha B and C. So what we want is this map where we can put vectors here and here, and we're going to map into C. So this is V cross V into C, where 1, we have V1 plus V2 W equals V1 W plus V2 W. V W1 plus W2 equals V W1 plus V W2. So it's a little familiar. 2, we want alpha V W to equal alpha conjugate V W, and V alpha W to equal alpha VW. If you remember, this is going to be linear in the second coordinate and conjugate linear in the first, which means you take the conjugate of your scalars. Just a note, warning, often conjugate linear in second coordinate. So often you expect this to be conjugate, and this not. Just a warning if you look at other functional analysis classes. But it's a metric. Okay, you want one more thing? It's called, this is going to be called positive definite. So, if V is an element of your vector space, you want V, inner product V, to be greater than or equal to 0, with equality if and only if V, little v, is the 0 vector. It's called positive semi-definite. Okay. Now, if your vector space has an inner product with an inner product and it is closed well, we need to talk about norms first. So vector space has an inner product, it's pre-Hilbert. Okay. Next. If we have an inner product, we have the Cauchy-Schwarz inequality. The absolute value of the inner product of V and W is less than or equal to VV to the 1/2 WW to the 1/2. Right? These are positive real numbers, you can take the square roots. If we let VV to the 1/2 be the norm of V, this gives us an actual Hilbert space norm, vector space norm. And so we get the inner product W is less than or equal norm of V times the norm of W. So we have a vector space norm. So if our vector space are pre-Hilbert space, so it has this nice inner product, is closed with, for pre-Hilbert space is closed, so any Cauchy sequence converges, any Cauchy sequence converges to a vector in our vector space under our norm, then V is a Hilbert space. So now we have the real structure we want to work with, Hilbert spaces. Okay, so now that we've built up, why don't we give some examples? So much erasing. Okay, getting sick of blue, switch to green. Cn is a Hilbert space. So how do we get this? Let V is going to equal lambda 1, lambda n, be an element of Cn. Happy vector. And W equal mu1, mu n, be an element of Cn. V, inner product W, can be the sum of lambda I conjugate mu I equal 1 to n. Or, this is going to be v star w. Or, ket v bra w, which we will also write ket v bra w. Lots of ways of notation. This is the usual physics broad ket notation. This is an inner product notation. And this is just looking at vectors. You'll get the hang of it as you keep working with it. Okay. Just a quick note. If we take bra v, ket w, this is vw star. This is now an element of mn, which we just draw off the second n if they're the same. And this is also the physics notation. And we'll jump between the two, because this is a math and physics class. Okay, so we have discussed more than just n-dimensional Cn. We had direct sums and tensor products. We would also like these to be Hilbert spaces. Well, if you're dealing with direct sums, it's easy. Let v1, v2 be in v, and w1, w2 be in w. Then our inner product from v direct sum w into c is going to take v1 w1 v2 w2, and this is going to be v1 v2 plus w1 w2. So we just add. Now, this is nice for direct sums. What about tensor products? Let v1, v2 still be in v, and w1, w2 still be in w. We're going to have inner product from v tensor w to c, b, v tensor v1 tensor w1, v2 tensor w2 is v1 inner product v2 in the v space, v vector space, Hilbert space, w1 w2, and w. So, as we would expect, we add for direct sums, we multiply for tensors. One word of caution. If you're looking at v tensor w, and v and w are infinite dimensional, this might only be pre-Hilbert. But the nice fact is it can always be completed. Okay, so this is our basic run-through of background vector space knowledge you should know. Now that was quick. You might want to consult your closest algebra book. But we will move on into postulates of quantum mechanics. So first, I will say a silly joke. What does a quantum duck say? One? Guess? Quark, quark. Okay, now that we've had our silly joke of the day, Postulates of quantum mechanics. So, our first postulate for an isolated system, isolated quantum system, so an isolated system is a system that has no interaction with the outside world. There is a Hilbert space H states, so let me say, a unit vector in H is a pure state, or a vector state. This is our first postulate, and now we actually have this Hilbert space. We want to measure it and see what's going on. Right? The state's great over there, but what's up with it? So, when we observe a system, it is no longer closed. It's no longer isolated. Right? An isolated space, an isolated system, has no interaction with the outside world. But we are physically interacting with that system. So it's no longer isolated. Now, how do we interact? This is a Hilbert space. Our interactions are linear operators. So, we will have a state space HS for our isolated system, and HO for our measured open system, open as it does interact with the outside world. And to measure it, we're going to act by an element, mi, or m, in the bounded operators from HO to HS. So, previously, we've been mainly working with finite-dimensional spaces. So this will actually be, this will often just look like matrices from HS, the cardinality of HS, cardinality of HO. Well, cardinality of HO, cardinality of HS. In full generality, it need not be, but for our discussion. Okay, so a measurement will be a set, a measurement of our space will be a set of operators, mi, where I is an outcome, I an element of some index set I, the set of all outcomes. If we are in state C an element of our closed space HS, then with probability Pi, which is going to equal Mi to C squared. So with probability Mi to C squared, we will see outcome I. So we will ending up in state. The state we will end up in HO is going to be MIC over the norm of MIC, because we must end up in a state, so it must be a vector length 1 here. But we said this is a probability, and we know things about probabilities. What happens if you sum all probabilities of a system? Well, one would hope you get 1. So 1 is going to equal the sum of Pi. I equal 1 to some n. Where n is the cardinality of I. Okay? But this, I equals 1 to n, is just the norm Mi to C squared. But this is a Hilbert space. We know what the norm is. This is the sum, I equal 1 to n, Mi to C, Mi to C. We can do one more thing. Take the adjoint to C, Mi adjoint, Mi to C. This is true for any state to C. Element of HS. It's true for all vector of norm 1. It's a strong condition. It is so strong, it tells us, well, we get C, the sum, Mi star Mi, 1 to n, of C. We get that this has to be the identity. Because if you act on anything else, you'll just move a little, which means you don't have inner product 1, because you already have 1. So, the sum, Mi star, Mi, I equal 1 to n, is the identity. It's a strong condition. So given a collection Mi where the sum Mi star Mi is the identity of I, we call this collection a cardinality of I outcome measurement, quantum measurement. Okay. Quantum measurement system. Now, let's have C1, Cn, say C be states in some Hilbert space, bidimensional Hilbert space H. We call C1, Cn perfectly distinguishable. So we call these perfectly distinguishable if there exists a measurement system mi, where 1 is less than or equal to I is less than or equal to some big N, where n is greater than or equal to n, and mi to ci, mi to cj equals delta ij, where this is the Dirac delta function, which is 1 if I equals j, and 0 if I does not equal j. So this is saying we have some quantum system, we have a set of states in our quantum system, and we can tell perfectly which of these states we're in. If we know we're in one of these states, and we hit it with this measurement system, we know which state we came from. Okay, that brings us to our first real theorem. A collection of states C1 up through to Cn is perfectly distinguishable if and only if the Ci is orthogonal to Cj for I not equal to j. Okay? So how are we going to prove this? So, suppose we have this case where Ci is orthogonal to Cj for all I not equal to j. So any two distinct vectors are orthogonal. Then let Pi be projection onto the vector space spanned by Ci, which we can also just write as Ci to Ci star. then I minus the sum of these pi's is a projection onto the space orthogonal to the span of these subspaces. Let's call this P0. Okay? Then we know that P0 Ci is just 0. Just the 0 vector. Because this is the orthogonal projection. And Pi to Cj, this is Ci star to Cj. This is Ci inner product to Cj. Things are orthogonal if their inner product is 0. So this is not 0 if and only if I equals j. And these are states, so if I equals j, this is Ci, which has norm 1. So one direction's finished. Now let's look at the other direction. Let mi 1 less than or equal to I less than or equal to big N be, so let mi be the set of measurements that perfectly distinguish these bases. Let's look at base 1 and base 2. We know we can always write base 2 equals alpha base 1 plus beta eta, where base 1 is orthogonal to eta. Then we get the norm 1 equals the norm of base 2. These base 1 and eta are orthogonal. Say norm squared. So this is just alpha squared plus also let eta, the norm, be 1. We can always change beta to make eta norm 1. So 1 equals C2 squared, because it's a unit vector, equals alpha squared plus beta squared, since these are orthogonal. Okay. So we know from hypothesis 1 equals the norm of M2 to C2. This equals the norm M2 alpha C1 plus beta eta. Okay? But M2 of C1 is 0. So this is just M2